Good day. Find your PowerPoint, the notes that say atomic radii and later on ionization energy. Radii is a funny word. It's the plural of radius, so we're looking at the many radii of all kinds of atoms and their ions on the periodic table. So we are down at a tiny level, often measuring things in nanometers or angstroms when we're talking about elements. And to simplify life, we like to think of atoms as being spheres, and they will have a radius. And the radius, the bigger it is, the bigger the atom's going to be. And we want to know some of the tendencies on the periodic table as we go across a row and down a column, or in other words, across a period and down a group. So we have two forces that work against each other to determine the size of an atom. So we have an outward force and an inward force. The inward force is that the nucleus has a positive charge that attracts the oppositely charged, negatively charged electrons. So they're trying to tug it in, make the atom smaller. Has to be an outward force. Well, we know like charges repel, and the electrons all have negative charges, and therefore they want to move away from each other. So to get the right sized atom for a given element, it's a balance of these two forces. So there are two tendencies for atomic radii. Across a period, atomic radii gets smaller. Now that will seem really weird because you would expect as you add more electrons they'll get bigger, but for certain reasons it actually gets smaller as you go left to right across the periodic table. Down a group it makes a lot more sense. As you go down and you have more layers of electrons, you get a bigger atom. So in your textbook you will have a table 11-1 that I've scanned here, so chapter 11, and the upper left of each element symbol or box will give you some sort of indication of the size. And we see as we go across the right, it gets smaller and gets smaller and gets smaller. Now you'll notice the noble gases tend not to have sizes listed. A lot of these sizes are determined from bonding, elements, maybe the same element or different elements bonding together. Later on we'll talk about the ions, and you'll see different sizes for the ions, but that's a different kettle of fish. So as we go to the right, the atoms get smaller, and as we go down a group, this is not surprising, it gets bigger as we add more and more layers of electrons. We'll go into the reasons for that in a strange thing I've called the brain sarcophagus. Now if you understand what happens to atomic radii, it's going to be the exact opposite for ionization energy. So first we have to define it. It says ionization energy is the amount of energy to remove one electron from an atom or an ion. So the units typically are kilojoules per mole. But what we see is ionization energy is inversely proportional to the atomic radii. So a smaller atom will have a larger ionization energy, and a larger atom will have a smaller ionization energy. And hopefully this makes sense. The size is coming from the location of the outer electrons. If those electrons are held tightly close to the nucleus, we have a smaller atom. That means a stronger force is holding them. It's going to take more energy to pop off an electron. On the other hand, if you have a larger atom with many layers of electrons, those outer electrons, which dictate the size of the atom, are not held as tightly. And therefore, it takes less energy to pop off an outer electron. And when we pop off an electron, we're always going to go for the easiest electron, the one that's held the least tightest. Here's another chart. And what it's doing here is, if you look over, here's your symbol, and what we're interested in are the ionization energies. Now, you're not going to memorize all these numbers, but we can plot a graph of that information, and what we see is, as we go from hydrogen to helium, first row, first period, gets bigger. As we go from lithium to neon, it tends to get bigger. There are little bobs up and down, and that has to do with part of the electron arrangement, the stabilities. But the overall tendency is that as you go, say from sodium to argon, that the ionization energy gets bigger. And in the brain sarcophagus, we'll give all those details.